Now we know that any RF system can be represented by an arbitrary impedance that has represented as ZL here, that has both resistance and reactance. That RF system is being fed by a transmission line of certain characteristic impedance called as Z0. For such an arrangement, we know what is going to be the reflection coefficient. It is going to be both dependent on the load impedance as well as the characteristic impedance. And that we already know that is going to be a complex number of the form gamma L that is dependent on ZL and Z0. It is given as ZL minus Z0 over ZL plus Z0. And this is the reflection coefficient right at this plane, where at this particular point where the load is being connected. So deriving the impedance, given a load impedance, to get the reflection coefficient, we can go ahead and use this formula to get the reflection coefficient, which is a complex number. The other way around, given a certain reflection coefficient, we can always recover back what is the load impedance that is giving such a reflection coefficient. We can invert this with having ZL as the unknown and writing it in terms of the characteristic impedance and the reflection coefficient. So both ways are possible. Turns out that in order to do this, each and every time could be cumbersome and tedious, and there is an easier way of doing this. We are going to look into that easier way of recovering the reflection coefficient given a load impedance, or given the reflection coefficient, recovering what is the load impedance through a simple chart which we call as the Smith chart. So if you take a look at a Smith chart, essentially what you can see is really a reflection coefficient in the complex plane. We know that reflection coefficient is a complex number. It has a real part and an imaginary part. A complex plane has the x-axis to be the real part and the y-axis to be the imaginary part. The special thing about the Smith chart is it can transform a particular load impedance to a corresponding reflection coefficient based on this transformation. And to do that, essentially the load impedance is normalized by a certain characteristic impedance Z0. We tell that the chart is normalized to that particular characteristic impedance Z0. If you notice here, the capital ZL denotes the load impedance. When you divide it by the Z0, you are normalizing it and you recover back this small ZL, which is dimensionless. The load impedance has the units of ohms, the characteristic impedance has the units of ohms, and ZL is normalized and it is unitless. So this particular transformation, we can see that this ZL has a real part and an imaginary part. Correspondingly, that maps to a complex number gamma L, which can be plotted in the complex gamma plane. In essence, a Smith chart plots the characteristic or the reflection coefficient in the complex plane. So let's say we have the reflection coefficient given to us and we want to know what is the load impedance that is giving such a reflection coefficient. For example, just for an example, let's say this particular reflection coefficient is having a certain angle, which is definitely more than 90 degrees here, maybe somewhere around 120 degrees, and having a certain magnitude, which is represented by the radius of this circle. It is essentially the magnitude of the reflection coefficient, the length of that particular vector. So this particular point in the gamma plane is being mapped to a certain resistance and an impedance. How do we know what is the resistance and the impedance? Analytically, we could go ahead and do this. Given a gamma L, we can go ahead and use this guy to figure out what is the impedance. So that is how we would do it analytically. But wouldn't it be easier if we were to look at this chart and directly get what is the resistance and the reactance directly? Turns out that that's possible, and that was invented by Mr. Smith. Turns out that this, instead of representing the reflection coefficient as circles in the complex plane, Directly, the Smith chart uses a set of curves called as resistance and reactance curves to recover back the impedance values. So what we see here is the overlay of the original reflection coefficient circles that we saw. On top of that, the reactance and the resistance circles that are being overlaid. So a real Smith chart is not going to have the reflection curves, but instead just the resistance curves. So with these set of curves, given any reflection coefficient, from the chart we can read what is the corresponding resistance and what is the corresponding reactance. So we are used to read in the Cartesian coordinate system, but a Smith chart is a transformation of this sort where we are mapping the reflection coefficient onto a particular resistance and a reactance that can be directly read from the Smith chart. And it is vice versa, meaning that if we are given a certain resistance and reactance, we can see the intersection of the constant resistance curves and the constant reactance curves to identify that particular point. The length of that vector gives the magnitude of the reflection coefficient, and the angle that it makes with the x-axis, the real axis, is going to be the phase of the reflection coefficient. Important thing to note is that the Smith chart is normalized always to a certain characteristic impedance, which is the characteristic impedance of the transmission line that is feeding the particular load. In this scenario, it is called Z0. To recover back the original resistance or reactance, we need to always renormalize or denormalize using the characteristic impedance. Given a small ZL, you can recover back the real impedance by multiplying it back by the characteristic impedance.